Assalamualaikum warahmatullahi wabarakatuh, my dear students. We are continuing Chapter 5 Chemical Bonding by learning Lesson 28 Hybridization. We are going to draw and explain the formation of hybrid orbitals of a central atom sp, sp2, sp3, sp3d, and sp3d2 using appropriate examples. Apart from valence bond theory, we need to know what is hybridization theory. Hybridization is a process of mixing the valence orbitals of an atom to form hybrid orbitals. So we need to be able to mix a set of valence orbital to form a new orbital called hybrid orbitals. There are 5 types of hybrid orbitals: sp, sp2, sp3, sp3d, and sp3d2. Let's learn the first one, formation of hybrid orbital sp. Sp orbital is formed when we mix the s orbital and p orbital. It will formulate 2 sp hybrid orbitals. The shape of the sp hybrid orbital is a linear and the bond angle is 180 degrees. So you can see here, if we mix one S and one P, it will become 2 sp hybrid orbitals. This is special for a central atom. Let's say we get BeCl2 molecule and we are asked to determine the hybridization of this compound. The first thing that we need to know is beryllium as a central atom. How many electron valence does it have? Before we do that, beryllium has 4 proton numbers. So I am going to draw here a simple molecular orbital diagram. 1s, 2s, and this is a 2p orbital, which is empty because since we have only 4 electrons for beryllium, the inner electron is this 2 and the outer electron or the valence electron are here. But since we have these empty 2p orbitals, okay, this is at ground state, we are going to look at the excited state. What is happening when beryllium atom is given energy to bond with 2 chlorine atom? So we look at the valence orbital because the inner orbital would remain. The 2 electrons would actually gain energy to go and excited to the empty 2p orbitals. So what happened is at the hybrid state, the mixed orbital of 2s and 2p is going to form an sp orbital, 2 of them. So that is why when we have beryllium, we're going to form 1 and 2 orbital sp, whereby these 2 mixed orbital, the hybrid orbital, is going to form a sigma bond with 1 molecule chlorine on the right and 1 molecule chlorine on the left. So there you go, the hybridization or the orbital overlapping for the compound beryllium dichloride. Another example for sp hybridization is for ethine C2H2. So firstly, we draw the skeletal structure of this compound. It's a linear like this, having a triple bond in between the carbon. So let's look at carbon. The ground state for carbon as a central atom is 2s2, okay, and then it has 2p, 1 and 2. And then for the excited state, what happens when carbon is given enough energy to combine and to form covalent bonding with another carbon and another 2 hydrogen, you would find that the electron will be excited to all the orbitals of 2s and 2p in a single spin. And then at hybrid state, okay, you're going to see that the S and P is going to mix and hybrid to become SP hybrid orbital, and then this 2 electron is going to stay in an unhybridized 2p orbital. This is unhybridized orbital. Okay, so you have 1, 2, 3, 4 electron each. So what does it look like? Okay, carbon has 1 sp, 1 sp over here. Okay, we labeled it sp, and then the carbon next to it would have another sp and one more. Okay, so this particular carbon, actually both of them would have 2p orbital. Okay, this is the orbital 2p, which is not hybridized. Okay, and here you're going to have a pi bond. Okay, another 2p orbital, if we can draw, it's over here, and another one is over here. So they would become another pi bond. Okay, so I forgot to label the sigma bond over here, and then we have another 2 sigma bond between carbon and hydrogen over here. So let's draw the s orbital of hydrogen with its sigma, and another one on this end. There you go. This is the orbital overlapping of C2H2, showing that the orbital of sp is formed. The second hybrid orbital is sp2. sp2 hybridization occurs when we mix s orbital with 2p orbitals. We will form 3 sp2 hybrid orbitals that will lie in the same plane, and the angle between the two of them is 120 degrees. As you can see here, the yellow circle is an s orbital, and there are 2 p orbitals in red that will mix, and they will become 3 sp2 hybrid orbitals, making the shape trigonal planar. If you are given BF3 and you are asked to draw the orbital overlapping for this compound, first that you need to draw is the geometrical shape, which is trigonal planar. And then we want to determine what type of hybridization occur for boron. At ground state, boron having 1, 2, 3 electron valence is going to have this kind of arrangement. But at excited state, the 1 electron at 2s is going to be excited to 2p, the second one, so that it is arranged one spin for each orbital. At hybrid state, 1 s orbital here will combine with this 2p to become sp2, sp2, sp2. 3 orbitals of sp2. Okay, so there's 1, 2, 3 electron there, and 1 electron, 1 orbital will be left empty. Okay, so how do we draw boron? Okay, and then the orbital sp2, then the other one forming 120 degrees between the two angles of bond and sp2, like this. Okay, what you're going to do next is F. F is a p orbital. Excuse my bad drawing. Okay, this is F. Okay, let me try to do a more symmetrical p orbital for F now. Okay, that's better. And this one. Okay, so can you see that sp2 is 1, 2, 3 bonding pairs attached to boron. This molecule is trigonal planar because it is on the same plane. Right. The next example is ethene, and the skeletal structure is given to you here. We look at the ground state for carbon, 2s, and for 2p we have another 2. All right. The excited state is the electron from 2s excited to a different orbital there. And then when it hybridizes, it will form the orbital sp2. The orbital sp2, 3 of them, 1, 2, 3, and then there is another electron that would stay at the unhybridized orbital 2p. So how are we going to draw this? Carbon would form a trigonal planar shape. Okay, and for this sp2, it is going to form a covalent bond, a sigma bond with the adjacent carbon. No, this is not where it's supposed to be. Sorry. It's supposed to be a planar, so it becomes like this. 120. Not so much. Let me do a different one like this. So maybe it's 120. So this is sp2, sp2. This is also sp2 and sp2. So this is 2 carbon atom. We have hydrogen, 4 of them over here. So we combine with covalent bonding here with the carbon. Okay, this is hydrogen, which is an s orbital. Okay, it will form a sigma bond here. So this is C2H4, and we can see that there are 3 sp2 hybrid orbital for each of the carbon in this compound. The third hybrid orbital is sp3. sp3 hybridization occurs when 1 s orbital and 3 p orbitals are mixed. These 4 hybrid orbitals are directed towards the 4 corners of a regular tetrahedral shape. All the angles become 109.5 degrees. As you can see here, the circle in yellow is the s orbital. It will mix with 3 p orbitals and it will become 4 sp3 hybrid orbitals, making the shape tetrahedral. Let's do an example of sp3 by using CH4 methane. For carbon, the ground state is 2 electron at 2s, 2 electron at 2p. Excited state, all the electron will go to each of the orbital of 2s and 2p in a single spin. And in hybrid state, it is going to form 4 sp3 orbitals, hybrid orbitals, and each of the electron is going to be making a covalent bonding, a bonding pair electron with hydrogen. So let's draw carbon with 1, this is the straight line, 2, this is the straight line, 3, this is the wedges line because it's big, and 4, maybe this is smaller one because it is dotted lines. So sp3, it is not necessary for you to label this, but in this explanation, I would want you to see it clearly. And it will form covalent bonding with hydrogen. So let's label all the 4 bonding pairs that will make up the sigma bond. So this is tetrahedral shape of CH4. So what happens if we want to draw the sp3 orbitals of ammonia? N as the central atom has 5 electron valence. 1, 2, 3, 4, 5. Just nice. This is at ground state. At excited state, it is going to stay the same because it doesn't have empty orbital. Hybrid state is, it is going to have a lone pair here at 1 sp3 hybrid orbital, and the rest is a covalent bonding with hydrogen. So what we are going to draw here is nitrogen having 1 sp3 orbital which has the lone pair, and then one straight line represented by this sp3 connected to hydrogen, covalent bonding, sigma bond, and this is the biggest one because we can see it very clear going towards us. Sigma, this is the wedges line, and this one is the line that you cannot see going away from you. So it is smaller. So we put, oh, that one is not really correct. So I'm going to draw the hydrogen atom again. Yes, this is the s orbital of hydrogen atom. This is the sigma bond. So we can see that this shape is a trigonal pyramidal of ammonia. The next example is for water. Let's look at the central atom oxygen. At ground state, oxygen has 1, 2, 3, 4, 5, 6. We apply Hund's rule here. Excited state, okay, it's not going to go anywhere, just the same. And then the hybrid state. Oh, what's that? Let me rub that off. Okay, the hybrid state is 1, 2, 3, 4. All 4 we called sp3 orbitals, and it would have 2 lone pairs here. So oxygen would have 1, 2 sp3 orbitals, and it would have the lone pair inside the hybrid orbital. Another sp orbital would be down here, and another one down there, that will form covalent bonding head to head with hydrogen atom here. So this is the band shape of water, showing clearly the hybridization of sp3 orbitals. The fourth hybrid orbital is sp3d. Hybridization of sp and d orbital involve the third period and beyond elements, because the molecular geometry cannot always be accounted by assuming only s and p orbitals. The formation of molecules with trigonal, bipyramidal, and octahedral geometries must include d orbitals in the hybridization concept. So for sp3d hybridization, we are mixing one s orbital, 3 p orbital, and 1 d orbital. We will generate 5 sp3d hybrid orbitals, and the molecular geometry would be trigonal pyramidal. This is how sp3d hybrid orbital looks like. If we are given PCl5, we know that the shape is trigonal bipyramidal. It has 5 bonding pairs of electron, and when we look at the phosphorus central atom, it has 5 valence electron at 3s and 3p. Double electron at 3s, singly spin at 3p orbital. At the excited state, we have 1, 2, 3, 4, 5 electrons going to the empty 3d orbitals. So the hybrid state is going to be 1, 2, 3, 4, 5. All these 5 are sp3d orbitals. Therefore, we draw P having 1, 2, 3, 4, 5 sp3d orbital. It's too big to label each 5 orbital now. So I'm just going to draw the chlorine atom having 5 sigma bonds with all the hybrid orbital that phosphorus has. Last one, this one, yes. This is the orbital overlapping for PCl5 having hybridization sp3d. The last hybridization orbital is sp3d2. sp3d2 hybridization is formed when we mix 1s, 3p, and 2d orbitals. It will generate 6 sp3d2 hybrid orbitals. This is how sp3d2 hybrid orbitals look like. Sulfur has 6 electron valence. So we draw 2 electrons at 3s, 1, 2, 3, 4 at 3p's. At excited state, it's going to be here 3s, 3p, and there is 1, 2, 3, 4, 5 empty 3d orbital, whereby we're going to write 1, 2, 3, 4, 5, 6. So the hybrid state is going to be 1, 2, 3, 4, 5, 6 sp3d2. There would be 1 electron each for this, so that it can form covalent bonding for 1, 2, 3, 4, 5, 6 sigma bonds over there. So how are we going to draw this? I need a bigger space, but I will try here. Sulfur 1, 2, this is bigger, 3, 4, 5 is smaller, 6. So this is all the 6 sp3d2 orbitals over here. And I'm going to draw the carbon. No, not chlorine. This is fluorine. Sorry, fluorine. And then it has the sigma bond over here. This one is a bit smaller because this is the dotted lines. This one is even smaller, the dotted lines. And this one is slightly bigger because it is the wedges line. This one is normal. Okay. And then finally this is should be big because it is the wedges line. Alright. So this is the octahedral of SF6 having hybridization sp3d2. How do we predict the hybridization of the central atom? Simple. We just count the number of lone pairs together with the number of bonding pairs at the central atom. For example, beryllium, the central atom has 2 bonding pairs, so it is sp. Bf3 has 3, so it is sp2. CH4, NH3, H2O has the total of 4 for lone pair plus bonding pair, so it is sp3. PCl5 has 5 bonding pairs, so it is sp3d. SF6 has 6 bonding pairs, so it is sp3d2. Here is your homework. Please fill in the third column of your A4 pages now. Alhamdulillah, we have finished orbital overlapping. Thank you for watching and see you again soon. Bye. Assalamualaikum warahmatullahi wabarakatuh.